this is the classic consolidation analogy that is used to explain how the water takes the load first as excess pore pressure, and then in time, as the water escapes, the excess pore pressure or load is transferred to the particles as effective stress. Okay, it's a very useful analogy, and it's the classic analogy from Terzaghi, I believe. Okay, so what we have here is a cup, essentially. Okay, so this is the cross section of a cylindrical cup, let's say. It's full of water. In here there is an internal or inner cell, okay, that has a spring, and there's a piston placed on top of the spring. Okay, and the piston has two little holes. Now at this point there is a gauge, a sensor, pressure sensor connected to the inner cell. So this pressure sensor is like a piezometer, basically. It measures what the pressure, water pressure, is at this point right there. Okay? So this whole thing is filled with water, so that the inner chamber is filled with water and the outer chamber as well, and that water is all interconnected through the drain holes, those two holes. Okay? And that is the initial condition or configuration of the experiment. Imagine that this is an experiment in the lab. So let's say you go to the lab and you find that on top of a table there is this little test going on. Okay? There's a little weight, a force on top of the piston, maybe a little disc that has been placed there, right? And you walk into the lab and you see this setup. You look at it and you see that the pore pressure measured here is hydrostatic. Now, how would you check that the pore pressure that is being measured here is hydrostatic at that point in time? Well, you would say, here's the point. What's the pressure head? The pressure head is this. The hydrostatic pressure head, well, in this case you would say, yes, the hydrostatic pressure head, because it's the distance from this point to this water table, right? And you would say, okay, that is 0.1 meters. 0.1 meters times 9.81 kilonewtons per meter cube is 1 kPa or so, right? So then you come here and you read, oh, 1 kPa, okay. That means that this system is in hydrostatic conditions. The water is pressurized only because of its self-weight. Fine. So you check that that is the case. Fine. Then you decide to mess with the experiment. Okay, so this is A. So then you come to B, right? B is this. You decide to do a little to mess with the experiment, with the setup, and you place another disc on top of the existing disc. Okay, that's what is denoted here by delta P. It's an additional load. This is not pressure. Huh? P is used for load or force. So there's another disc that you place. You decide to mess with this, and you place another disc on top of the initial disc that was there. So it's P plus delta P. This is what you impose. Now, initially when you place the disc, what do you see? Okay, what do you see? Well, you see nothing. All you see is that this needle moves up. Okay, but you do not see, initially you don't see the piston moving. And you say, well, hold on one second, what's going on? The water is at the same location as before, but there's an added pressure here. This moved up. There's more pressure. What's going on? Well, what happens is that this disc, this second disc that you place here, this delta P, is initially carried by the water. No, the water in here. Sorry, I went like that, but it's the water in here because the piston is on top of this water, right? So the water in here is carrying that disc. At that moment, the moment you place the disc on there, the water carries it. So the additional pressure registered by the sensor is the excess pore pressure. How would you calculate it? Well, if you added delta P, which is a force, and a pressure was registered as a consequence of that force, then the pressure is equal to that force divided by the area of the piston, the cross-sectional area, right? So the delta P divided by the A is the stress imposed vertically, that is of course carried by the water as a pressure, because water doesn't really carry stress in, that is, water carries stress of course, but it does so as pressure, as a stress that acts the same in all directions. That's pressure. So the UE that is generated at that point in time is delta P, the force, divided by the area of the piston. That point in time we called it, the book calls it T0, we call it 0. Okay, that's time equals 0. Sorry, this is time equals 0. The time at which you enter the lab and you see this experiment going on and you say, okay, I just came in the lab, nothing's going on, that's time equals 0. We call this time 0 plus. That is the time at which the load is initially placed. You place the disc, the pressure goes up, and it goes up by an amount equal to that load divided by the area. That is time equals 0 plus. That's just a way to label it. Okay? So, why doesn't the spring squeeze? That is, why doesn't the spring carry the load? Why is it that the water is the one that carries the load? Well, we already talked about this kind of implicitly before. We said that water has a very high stiffness, right? In fact, some people say that it's incompressible, even though it is compressible, but it has such a high stiffness that we say, you know what, it's incompressible. Well, it has a high stiffness. In fact, the stiffness is higher than that of the spring. If the stiffness of this spring were higher than that of the water, then this wouldn't happen. The spring would carry the load. But because the water has a higher stiffness than the spring, then it carries the load imposed initially. Okay? Let me go back to solid mechanics and make an analogy here. Let's say that you have large spring, a wimpy spring, meaning the stiffness is low, another spring that has a high stiffness, and then another one that has low stiffness. Okay? And you place a force here. Do you think these four springs carry 1/4 of this force? This force is P. Do you think this spring carries a fourth of P, this one a fourth of P, this one a fourth of P, and this one a fourth of P? No. The springs that are stiffest carry most of the load. Okay? And so that is something that applies to all materials. If there is a system of materials together that make a composite material like soil, and there is a load applied, then the component that has the highest stiffness will carry the load initially. Okay? And the water has a higher stiffness than the assemblage of particles. So remember, when we talk about soil, we talk about a structure of particles. That structure of grains that move relative to each other, that can move relative to each other, that packing has a lower stiffness than water. Now, a particle, the material that makes a particle, like quartz may actually have a higher stiffness than water. But what matters is not what makes the particle. What matters most for the comparison of stiffness in the soil is the assemblage of the particles, the fabric, the stiffness of the fabric, versus the stiffness of the water. In all soils, the stiffness of the water is higher than the stiffness of the fabric. Now, sometimes the grains are cemented, and in that case, then they may start approaching each other, etc. But typically, when we have soil that is not cemented, I would say all the cases of soil that are not cemented, the stiffness of water is higher than the stiffness of the fabric. Okay. So here in this slide, the spring corresponds to the fabric. It's mimicking or simulating the fabric, and the water is simulating the water in the soil, in the voids. Okay, now After some time, that is, let's say 20 seconds after you place this disk and register this UE, you look at the gauge. Okay, so this is time equal to, let's say, 20 seconds. You look at the gauge, and the gauge is coming back. It's basically registering a lower pressure than that registered initially when you place the spring. Sorry, not the spring, the disc. Okay? And what you see is that the spring is a little bit deformed, a little bit squeezed. You can see that the spring here and here is the same, but here is a little bit squeezed. So what's happening is the consolidation process is taking place. The water is escaping through the drain holes because it's pressurized, in addition to hydrostatic. The water wants to be pressurized at hydrostatic. When you pressurize it at a higher pressure than hydrostatic, that is, if you pressurize it with an additional pressure, the excess pore pressure, then it wants to minimize the energy condition, and therefore it wants to escape to achieve a hydrostatic condition where the pressure is only hydrostatic. So the water is pressurized by UE, and it says, you know what, I need to get out to go back to hydrostatic. So it escapes through these drain holes, and as it does that, then the piston is able to move down as the spring squeezes. Because the spring is squeezing, you know that there's force in the spring. So the excess pore pressure is being transferred, the load, that is the excess pore pressure, is being transferred to the spring, from the water to the spring. As the water escapes, the excess pore pressure goes down, as you can see here. It's just a fraction of what it was before, and the spring begins taking the load that you placed, the disc. Okay? At time equal, here it says T2, we're going to call this time equal time end. Okay? The spring is fully compressed, okay? And the pore pressure has gone back to hydrostatic. So not 20 seconds, but maybe 120 seconds later, the water that needed to escaped into the bulk fluid, and doing so, the load was transferred from the water in here to the spring. So when you come in here and measure the pore pressure, it's the same as it was initially before you place the additional load. Okay? This is the process of consolidation. Here there's nothing going on. Here you place the load and consolidation begins. The UE is generated, and in time it is dissipated by the water escaping, and the load is transferred from the water to the spring. So eventually, if you recall that the spring is a simulation of the fabric of particles, and that the water in here is the pore fluid, then eventually the pore water pressure is hydrostatic, and the load is carried fully by the fabric. And that's the condition that we eventually want, because we eventually want all our structures to be carried by the particles. Okay? But it may take some time for that to occur. And that time is T end. Okay? In this case, it may take 100 seconds. In this case, in another case, it may take 100 days. What is going to dictate this time? Well, as you probably have guessed correctly, is the size of these drain holes. If the drain holes are very, very small, then it takes a long time for the water to escape, because the voids are small, not the voids, the drain holes, which are essentially mimicking the hydraulic conductivity of the soil. Okay, so if the holes are small, that essentially is meaning that the hydraulic conductivity is low. In that case, it will take a long time for this to happen, this whole process. But if the drain holes are huge, then of course, as soon as you place the disc, the water is going to squeeze out easily, and it will take less than a second, let's say, for the UE to be dissipated, mean reduced back to zero. You may not even see the UE. In that case, you have a drain condition. Okay? Okay, let's transfer this slide here, this physics here. Let's transfer that physics to what happens in the field for a soil mass. Okay. In fact, for a point in a soil mass. Why for a point? Because here we're plotting stresses, and stresses act at a point. So here we have our site. Water table is there. Here's a point that we're interested in. Here's rock. And we are going to construct a fill on top of the site in layers. Okay, so what we want to monitor here in this, with these plots, is the total stress at this point, total vertical stress. Remember, we talked about the fact that we are considering vertical stresses because of the fact that the deformation due to consolidation will be a vertical one. We have the pore pressure, total, and the effective stress, vertical, which is what the waters carry, what the particles carry. So this is what the particles feel at this point. This is the stress that the water feels at this point, which is a pressure, and this is what both of them feel at this point. So we get to the site before we start constructing, and we look at the point and we say, okay, we can calculate with the gammas, etc., and the location of the water table. We can calculate the total stress, the pore pressure, and the effective stress at this point. And those are respectively 130, 60, well, 65 and 65, let's say, right? Because this value plus this value is equal to this value. This is time, okay? So we get there, we're walking around the site, and of course, those three parameters are constant at this point. Then we decide to begin construction, okay? Well, that means that we start adding load, so the total stress starts going up. So that's the construction period of time. Okay? It takes 5 days to construct this field, let's say. This is 5 days. And so the delta sigma imposed when we finish is the gamma of the field times the thickness of the field. Just like we have done for layers, for all layers when we calculate total stress, right? Gamma times the thickness. So eventually the total stress is, 225. Now, what happens to the pore pressure at this point? Well, initially before construction we said it was 65, right? Now I'm placing numbers here just for kind of I'm adding the 65, 225 here to the discussion just to have some kind of numbers going on in 5 days, etc., right? But what matters is the trends. So initially, yes, we have some value, right? 65 or whatever, before construction. And then we see, let's say we had a sensor in here somewhere that would tell us the pore pressure. We see that the pore pressure rises during construction. And it achieves the highest pore pressure level, 160 or whatever, at this point when we finish. Okay? Now what does that mean? That means that the load that we have placed on the site is carried at this point. This load is carried at this point as excess pore pressure. So any pressure registered at this point above the hydrostatic one, which is this, is excess. Of course, is in addition to hydrostatic. So if I ask you, is this a drained or an undrained condition? Clearly you would have to say this is undrained because UE is not zero. We can actually measure it here. Look at it. Now when we finish construction, then we're now standing at the site over here, right? We're standing there. And so there's no more construction going on. So the water now has time, let's say, to escape the voids, and the soil compresses, all this soil squeezes as the water escapes. Okay? It's this basically, it's this, but at for trillions and trillions of grains. Okay? So as the water escapes, then the pore pressure excess dissipates and goes back to hydrostatic, just like the case of our spring example with the piston. Same thing. Now, these values minus these values, sigma minus u is sigma prime, right? We know this by heart. That's Terzaghi's effective stress equation. We use it all the time. So this plot minus this plot gives us this plot here, which is what the particles feel, which is what's most important. So the particles initially are feeling 65 or so, and as the pore pressure drops, because the water escapes, then the spring or the fabric, the particles, start carrying the load that you impose during construction. And eventually, at some time, T end, at that time, the effective stress becomes constant and higher, of course, than the initial effective stress before you construct it. That difference is equal to this. Right? Because eventually the particles at this point carry the load that has been placed above. Okay, that is the consolidation process in the field. Now, a typical question that is formulated in the minds of students is based on the concept of the water escaping. So the students have kind of a hard time saying, okay, or understanding, where does the water go? How is it that the water escapes? Well, the water essentially doesn't escape and move somewhere else, out of the site or something. No, the water is still there. What moves relative to the water is the soil. So let's understand this a little bit with an analogy, or not an analogy, an example. Okay, so let's say that we have a site. Let's say this is high plasticity clay or something like this, and the water table is at the ground surface. Okay, and then we place a fill. Now, if this is clay, and there's going to be a fill placed, or we actually are constructing or placing a fill, okay, that's the tree to indicate that this is the ground surface and the water table is there. That's the fill. We place it there. We know that because this is clay, its permeability or hydraulic conductivity is very low, so we can expect on drain conditions, and we can expect the clay layer to squeeze, to consolidate, okay, but not immediately. It will take time for it to do this because the hydraulic conductivity is low. So consolidation will take some time to some long time, maybe months, okay, to finish. Now, eventually, the layer is going to end up maybe this thick, okay? So the initial thickness, which is denoted typically by I, is that, and then the final one is that, and this is the consolidation settlement, okay, which we're going to learn how to determine later on. It's very important. Now, what that means, if there's a consolidation settlement because of the placement of the fill, what that means is that the fill is no longer going to be here after you finish constructing it, right? The fill is going to end up there. And this will be, if the fill doesn't consolidate itself, this consolidation is essentially the same as this one. That is, of course, if the fill doesn't deform, but the fill does deform, etc. But we are assuming that the fill is, let's say, incompressible for this just example, because we're trying to understand where the water goes. Well, the water doesn't go anywhere, the water remains there. But relative to the location of the interface between the fill, the new interface between the fill and the clay layer, remember the clay layer was this big, now it's this big. It was this big or thick, and now it's this thick, meaning after consolidation, it becomes thinner. So the water that was initially here, right? Look at the water table, remains there, but now it's higher than the interface between the clay layer and the fill. So the water does flow, but it flows accompanying the squeezing of the soil. Okay, but eventually it ends up at the same level, unless there is dewatering. If you come in here with a pump and reduce the water level to down here, then we have another problem, right? That's another type of problem. That's what I'm saying. But the water essentially just remains there, and even though there's local flow from pore to pore, etc., the whole water mass, as denoted by the water table, remains there. Okay, what changes is the location relative to the interfaces, because the soil deforms. Okay, and so to summarize what we have learned into the main, very important lines, let's say text lines or sentences. Consolidation involves a gradual transfer of stress, okay, of a load from the pore water to the soil grains. So the pore water initially carries the load that is imposed as UE. So at time equals 0 plus, which is the moment where the load is placed, the UE is equal to delta sigma, the load. Okay? And then at time equal T end, the UE is 0, and the grains, particles, are the ones that carry the load. Okay, so at time equal T end, the pore water pressure in excess of hydrostatic goes to 0. The hydrostatic pore pressure remains unchanged at this time. Okay, and at all times, the hydrostatic pore pressure is just a value, which is the self-weight of the water converted to a stress, right? But we're talking about excess pore pressure. At time equal 0, the excess pore pressure is the load, 0 plus, the moment where the load is placed. That incipient moment is 0 plus, and that's when the excess pore pressure is equal to the load. At time equal T end, which is at the end of consolidation, after the soil has squeezed and the water has squeezed out of the soil has compressed and the water has squeezed out of the voids for the soil to achieve that new configuration of fabric, then the excess pore pressure is 0 because the load has been transferred to the particles. So the particles now feel what they were feeling before, so the initial effective stress, that is before construction, plus the load that was imposed, that was initially carried by the water, now it's carried by the particles. Okay, that is very important. That is the key to everything, actually. So, because there is a change in effective stress, then that is what conduces to consolidation. So the deformation of the soil can only occur if the particles feel a change in the stress that they feel, right? So this here is very important to understand that this summary this sentence is the summary of the concept, which is to understand that consolidation begins immediately after the load is placed. So the load is placed, meaning the fill, for example, is constructed on top of a site. Immediately the pore pressure is generated, the excess pore pressure is generated, and immediately, because the water is pressurized, immediately the water begins to squeeze out, and immediately the particles begin to receive that load that is transferred by as the water escapes. Okay, so the consolidation doesn't decide to start when you finish construction. Okay, that's something that many students believe is the case. Many students believe, because of this slide particularly, that consolidation, which is essentially this curve here, these two curves, many students believe that that's when consolidation begins. No, consolidation begins at the moment you place a grain on top of the existing site. At the moment you place the first grain of the first lift or sub-layer, at that moment the water carries the load and then it escapes and transfers it to the grains. Okay? It does so slowly, but that triggering of the consolidation effect or consolidation process occurs immediately upon loading. Okay? So consolidation doesn't begin at the end of construction. It occurs throughout construction and then after a period of time after construction, provided that the condition is undrained, of course. Okay, now just to end this part of the videos of consolidation, let's look at this plot. We said that here, well, we didn't say what soil we have. Let's say we had a silt. Okay, let's say we had a silt with low plasticity silt. Okay, that is a soil that we can expect will suffer undrained conditions when we load it with typical construction practices. So it will consolidate in time. It will take some time to consolidate, not just seconds, like it does for sand or gravel. Okay, now let's say that we monitor the excess pore pressure dissipation or reduction in time, and we get this plot. Now, what would you think, or what do you think the plot would look like if we had a clay, low plasticity clay, to keep the L's the same, whatever? Okay, how would this look like? Would it look the same? Would it drop faster or would it drop slower? Well, if you think that it will take longer for the pore pressure in excess to dissipate, you're correct, because clay has a lower hydraulic conductivity than silt. And the hydraulic conductivity dictates the drainage rate. So if the drainage rate is very low, then you can say in quotes that the system is very undrained, okay, which means that it will take a long time for that UE to go back to zero, because it will take a long time for the water to be able to escape those pores that are very small for clay.